You have landed at the most important chapter in all of mechanics. You will learn what is force, what it can do, what are its effects, and the concept of inertia, of rest, of motion. However, nobody tells you that it has got very limited applicability. I will tell you that. And a lot of people think that the body will always move along the direction of the force acting on it. I will tell you that that is not always so. So essentially, we are going to cover Newton's laws of motion, and I don't come to the law straight away saying, look, here's the law, learn it, understand it, mug it. I build it up by observing what is happening around us, what rules nature follows, and what is the historical perspective of how people came to this law, how Newton came to this law. Welcome to the portals of real learning. Don't skip and listen very carefully. Welcome to the chapter on laws of motion. And I'm welcoming you to the amazing world of physics because this particular chapter, which is the laws of motion, is the cornerstone of all classical mechanics. A lot of things are based on these laws. So make sure that you understand the concepts very well. We are going to talk about inertia, the concept of force, Newton's three laws of motion, and also we'll get introduced to a new concept called momentum. All right, so let's begin. In kinematics, we studied motion by analyzing the various parameters like speed, velocity, displacement, distance, and acceleration. We didn't discuss what causes that motion. In this chapter, we are going to discuss that. What causes a motion? What makes things move? Or what makes a moving thing change its motion parameter, change its velocity, change its direction? What causes that? Now, the fundamental thing that all motion is relative, all that principle does apply. So we're going to look at everything from the ground frame of reference, that is a frame of reference that is fixed to the ground. And that, by the way, is called an inertial frame of reference. We will understand what is the meaning of inertial frame of reference. But think about it. What makes a thing move? A football on the ground doesn't start moving by itself unless somebody kicks it. Its velocity was zero. The kick imparted a certain velocity to it, right? Without the kick, it doesn't start moving automatically. A baseball thrown at a batsman, the ball is already having some velocity. The batsman hits the ball, due to which the ball changes its direction and maybe also changes its speed. That means the velocity has changed. In both cases, the velocity has changed. In the first case, the velocity was zero, then it became something due to the kick. In the second case, the velocity was something and it became something else because the batsman hit it. If the batsman had not hit it, the velocity would not have changed. A drop of water falls off the leaf. Once it becomes too heavy, why does it fall down? Its velocity is again changing from zero to something. And there's a heavy box on the ground, you can pull it. A heavy box is being pulled with a rope that also changes the velocity. In all these cases, the common thing is that the velocity has changed. Whether from zero to something or from something to something else, there is always a change in velocity. So when the motion starts, it goes from zero to something, the velocity goes from zero to something, that is the cause of the motion. And change of motion means change in the velocity. The cause of all motion or the cause of all change in motion is what we call force. And force causes a change in velocity. In other words, if there's no force, there is no change in velocity either. Long back, Aristotle, the Greek thinker in BC era, they used bows and arrows, and the experience was that once the arrow leaves the bow, it stops, it slows down and stops and falls to the ground. And Aristotle said that an external force is required to keep a body in motion. Once the arrow leaves the bow, in order to keep it moving, we need to keep applying an external force, otherwise it does not continue its motion. And he said that air was pushing the arrow, etc. Now we know it is wrong. So 1500 years later, Galileo proved him wrong, than Italian astronomer. And he did some experiments. He made a block slide down an inclined plane, and he found that the speed increased. He gave a speed to a certain block on an inclined plane, and he found that it retarded. But if he gave a speed on a horizontal smooth floor, then there was no change in the velocity. There was no acceleration. So what can we conclude from this? The speed was zero, it picks up some speed. Here the speed was something, and then the speed reduces. Ultimately the body stops at some point, and here there is no change in the velocity. So the common thing is that here in this case there is no external force on it that will stop it. In the horizontal direction there is no external force. We are talking of a very smooth floor. But even if this plane is very smooth, there is an external force due to which there is a change in velocity. He also did experiments taking a marble and making it slide down a bowl, and he found that if the bowl is very smooth, whatever height it was dropped from, it rises up to the same height, stops, and then comes back. Even if the slope of this thing was made milder, the height was still the same. The height was still the same, and if there was nothing, then it would acquire a certain speed, and that speed will keep going on and on. The conclusion was that if the body is not changing its velocity, then there is no net force on it. Similarly, a body which is at rest, the velocity is zero and that doesn't change. The main thing is change in velocity. A body at rest has zero velocity and that doesn't change if there is no net force on it. And the major conclusion was that whether you talk of the state of rest or a state of uniform motion, that is constant velocity, they are equivalent states. There is no net force on them. They are equivalent states, right? So if you look at a ball that is set into motion, it will keep moving with that same velocity perpetually. But we do find that it does stop. That is because of some external force like resistance of the air or the ground, which is not very smooth. The ground is exerting a force which we call friction. Otherwise, it would keep going on and on. If a body is released in the space where there are no masses nearby, if it is released in space with a certain velocity, it will keep going in a straight line with the same speed, no change in speed, no change in direction, no change in velocity. Why? Because there is no other body around it to exert an appreciable force. That was Galileo's correction. That means, he said, Mr. Aristotle, no external force is required to keep a body in motion. If there's no external force, the body will not change its motion. It will keep going on and on. And why something stops is because of the presence of external forces. That was a major learning, actually. So Newton was a guy who formulated his three laws of motion, right? So far, what we have learned is if a body is at rest, it will remain at rest unless an external force is applied. If a body is moving with some velocity, it will continue to move with the same velocity unless a force is applied on it. With these two learnings, we can state the first law of motion. If a body is in a state of rest, it will remain in that state. And if it is in a state of motion, it will remain moving in the same direction with the same speed, that means same velocity, unless an external force is applied on it. That is Newton's first law of motion. No motion happens by itself unless there is a force on it. There is no change in motion unless there is a force on the body, an external force. And this law is also called the law of inertia. So what is inertia? It is a tendency of a body to resist a change in its state. If it is in a state of rest, it will resist any change to it. If a body is having velocity, It will resist any change in velocity by virtue of its inertia. And inertia is linked to the mass. More the mass, more the inertia. Let's understand this. We'll come to that part, but now let's define force itself. It is that physical cause which changes or tends to change either the state of the rest of the body or the state of uniform motion of a body or even the shape and size of the body. It is that physical cause. That is a definition of force. It is a push or a pull. It is a vector quantity, and the unit is aptly called Newton in honor of the scientist who did a lot of work in this area. But why do we use the word tend to change? Well, you can apply a force on a body, but it may not change its state. Example, you push a wall, it remains at rest. Why does it not change its state? Because it has got its internal strength, which is elastic forces, which prevent any change in its shape or size or even make it move or something. But you are applying a force. So therefore, we use the word tend to change. A body at rest will continue to be at rest. A body moving with a certain velocity will continue to move with the same velocity unless acted upon by a force. And force is a vector, and vectors, when they added, can result in a null vector. That means if many forces are acting simultaneously on a body, the net result may be zero. So the net force may be zero. If a body is in a state of rest, we can't necessarily say that there's no force on it. All we can say that there is no net force on it. Similarly, if a body has a constant velocity, then there is no net force on it. If there was a net force, then its velocity would change because force causes acceleration, force causes change in velocity, right? So let's talk of the concept of inertia. We said it is resistance to change, right? If a body can resist a change in its state better, then it is said to have more inertia. Now, what is the meaning of better? Or how do we measure or observe this betterness? Or how to observe this resistance to change? Suppose you kick a football and you kick a rock. With all the power that you can muster, the football picks up a large speed, but the rock probably doesn't even move. Or even if it moves, it acquires a very small velocity. Why? Rock has more mass. The rock gave greater resistance to your kick. It has got greater inertia on account of its greater mass. The mass is linked to inertia. Similarly, if a cyclist is going, we can change the path of the cyclist by pushing him sideways, but we can't do the same thing with the truck because the truck has got a greater mass and it resists any change in its motion better. That means you need to apply a larger force to make the truck change its motion. It has got more inertia. Inertia of rest is how hard it is to make a body move, and inertia of motion is how hard it is for us to change the velocity of the body. How hard means what big force we need to apply. Bigger the force that we need to apply means bigger the inertia. Some examples of inertia, you shake a tree, the leaves fall off. The leaves don't want to change their state of rest. The tree is shaking, the leaves don't want to shake along with it. If the tree is shaking, the branch is shaking, then the branch breaks off and the leaves fall off. You take a carpet and you can remove the dust by hitting the carpet on the ground. That hitting removes the dust. Again, inertia. You have some carom coins. With the striker, you hit the bottom coin. Only the bottom coin moves and all the other coins do not move at all. That is also a demonstration of inertia. But just understand this much, that inertia is linked to the mass. How far this concept of inertia can be taken, that is rather limited, and I'll show it by an example. Let's also discuss inertia of motion. This was inertia of rest. A cyclist is going. If he presses the brake, it doesn't stop immediately. It has got a certain mass. It doesn't stop immediately. If you jump off a train, you don't stop immediately. You fall off. You got to keep running for some distance. Otherwise, you're going to fall off. Because you were running, you had an inertia of motion. The velocity of yours cannot change immediately because of your inertia, because of your mass, right? If you're in a bus and you get onto it and the bus is going at a constant velocity, suppose the driver presses the brake, you fall forward. You were already moving, the bus is stopping, but you are not stopping because of your inertia. Therefore, you fall forward. But the concept of inertia doesn't go very far. Only thing that you need to understand is greater the mass, greater the resistance to change that it offers. Here is an experiment. There is a coin kept on a cardboard, and the cardboard is placed on a glass, and we give a sharp hit to the cardboard. The cardboard flies off, and the coin falls down. The cardboard flies off because of the sharp impulse that we gave to it. The coin doesn't move along with it, and a lot of people will say it is only due to inertia. But no, here it is not a concept of inertia, it is a concept of insufficient friction. If the friction was sufficient, then the coin would have moved along with the cardboard. Same thing applies to the carom board coins example, that when you hit the bottom coin gets an impulse and flies off, the other ones don't go along with it. They could go along with it if the friction was strong enough. So this is an example of insufficient friction, really. All right. We understood what force is. So one thing was it can change the state of rest or of uniform motion, and the second was it can change the size or shape of a body. Let's take the first case. A football is there, you kick it, you can start the motion, or if it is already moving, you can stop it by bringing your leg in front of it, right? A cricket ball is moving, you hit with the bat, you can glide the ball towards the third man region, right? You are changing the velocity, the direction you're definitely changing, maybe also changing the speed. So the state of rest has been changed, the state of uniform motion has been changed. Now, force can also change the shape or size of a body. If you take a balloon and you press it from all sides, then the net force on it is zero, therefore the balloon doesn't move anywhere. But because you're applying force on all sides, it becomes smaller. The size changes. Or you can take a Pepsi can and press it, you can change the shape of that Pepsi coin. The net force is zero, therefore it doesn't move, but it can change the shape or size of the body. Force can do all of these things. If you talk of starting or stopping a motion, suppose a body is stationary. And what is a rigid body? That is important. Rigid body is one whose shape and size can never change no matter how large a force you apply, which is actually an idealization. There is no such thing like a rigid body. Everything can be broken if you apply a large enough force. Everything can be bent if you apply a large enough force. Anyway, we take this ideal case of a rigid body. If it is stationary, but it is free to move around, and if a force is applied on it, it begins to move in the direction of the force. Now, multiple forces may be acting on the body. If there is a net force, and the net force is a summation, a vector summation, because force is a vector, the net force is a vector summation of all the forces, and then the body starts to move in the direction of the net force. You know, this famous legend of the apple falling on Newton's head. The breeze was there, therefore the apple broke off, and then it falls on his head. It was attached to the branch, it was not falling because the branch was pulling it with some force. Moment the branch breaks off, then the earth is attracting it, and that is called the weight of the apple. Therefore, it moves along the direction of its weight, which is vertically downwards and falls. A ball is going, and the fielder stops it. Right? He is stopping the motion by putting his hand in front of the ball. He exerts a force on the ball to stop the motion. Horse pulling a cart, the horse presses the ground, pushes the ground backward and the ground pushes him forward. We'll learn about that particular thing later, but basically, horse is pulling the cart by exerting some force on the ground that starts the motion. And again, a kick starts the motion of a football. So this was starting or stopping a motion, right? Now, force can change the motion itself. That means change the speed or the direction or both. So let's see some four cases. The last discussion was starting or stopping a motion. This discussion is that there is a motion, and if there's a force, then it can change the speed or direction or both. It will definitely cause a change in velocity. Unless, of course, there are other kinds of huge forces which prevent this force to do its job. That is why we use the word tend to change. Let us take some simple examples. Suppose a body is moving with the velocity v to the right and a force is applied in the same direction. Then the speed increases, but there is no change in direction. Like a boatman, suppose the boat is already going with the speed v and the boatman uses his oar to push the water and the water exerts a force forward. Therefore, the boat speed increases. Suppose the force is opposite to the velocity, then the speed decreases and there's no change in direction. Like if a body is given a speed on a floor and the floor is rough, so there's something called a frictional force which opposes that slipping, acting opposite to the velocity. Therefore, the body stops. Friction is stopping it. Please note in both cases there is an acceleration. Suppose the force is perpendicular to the velocity. That is very interesting. Then the speed doesn't change, only the direction changes. Like you take a stone tied with a string and the other end is on your finger, you can make the stone go around in a circle with a constant speed, but the velocity, which is tangential to that circle at all times, is changing its direction. The speed doesn't change, but the direction or the velocity changes. And if the force is at some general angle to the velocity, that velocity is to the right, the force is at some angle, then we can break down this force into two components, vector components. One is a parallel component, another is a perpendicular component. The parallel component is going to increase the speed, and the perpendicular component is only going to change the direction. So in this case, both speed and direction will change, right? You can see here, in general, a batsman hits a ball, he can hit it towards mid-wicket. So direction is changing, also the speed is changing. But the point is, in all cases, there is a change in velocity. Force is the guy which causes a change in velocity, or rather, force is the guy who causes an acceleration. Clear? Changing the size or the shape. Well, rigid body is one whose size or shape can never be changed. So there's no such rigid body in practice. But let's talk of practical cases of a non-rigid body which is not free to move. Then the size or shape can change. Example, spring. It is hanging. Now, if you apply a mass over here, then the weight of the mass is acting downwards, which elongates the spring, changes the length. If you take an iron rod and pull the iron rod with equal and opposite forces, these are vectors. Two equal and opposite forces will result in no net force. So the rod is not going to move, but there is going to be an elongation indicated by this red part. Size has changed. Balloon, again the size has changed. If you have some gas in a piston and you press the piston, then the volume is changing. Okay, volume is changing. That means the overall size. Okay, it's not size of the gas, but we can only say that the volume of the gas is changing. Force can do three things: change the state of rest, change the state of uniform motion, or change the shape or size or both of the body. All right. So that is it for this session. In the next session, we are going to learn about the second law of motion, and we are going to get introduced to a wonderful concept called the concept of momentum. So this chapter is extremely interesting and it is extremely important because that is a cornerstone of all mechanics. A lot of things are governed by these laws of motion. Okay, guys.